Doc is here. I can't believe we're on day 4, but that's great. And again, lesson 10. And we're at section 2.2 in the book. You should have 2.8 if you had the other book. Now, we're going to take a look at the derivative as a function. So first I'm going to use some of the illustrations from the book. Here we have a function of f. If I ask to graph what the derivative looked like, now keep in mind the derivative at every single one of these points has a value, a slope value. So instead of having my point be 1, 1 right here, I would have this point be 1, whatever the value of the slope is. And that would create a new graph. So let's take a look at that a little closer. This better illustrates it. Notice where I change direction. I go from decreasing to increasing or increasing to decreasing. Those areas are called critical points. And when that shift takes place, there's a place where that line is a horizontal tangent line where the slope is 0. So that would mean at some point right here, looks like maybe about 0.4, there's a point 0.40 on the graph of the derivative. I'll say that again. So there's a point right here. I'm going to estimate. Looks like it's probably around 0.4, which would be your x value. Then your y value would be what the slope is, 0. So here it is. Now before that, notice as I come down, I'll grab my pencil. I'm going to put that many marks on this because I'll be writing all over it. I grab my pencil. If I look here at slopes, all of these slopes on this side are negative. So that means all of these numbers are going to have negative values. Up here is steeper than down here. So my slope here is going to be way down here. So again, my slope at, we'll say, negative 0.25 has a very steep number to it because the slope is steep. Again, we're using the slope as a point. So that's why this goes from negative slope, negative slope, negative slope, negative slope, negative slope. Up, I hit 0 here. And now, as soon as I hit 0, I'm turning, and now my slopes are positive. So they're positive numbers. So my slope, for instance, at 1 is going to be a positive number. And you can see it starts to get less steep after that point. And that's why it starts to come back down. And then we have another point 0, which is right here. And we continue down, and now we have negative slope again, negative slope. Again, drawing the tangent line slopes here. Then we come around this curve, and it's still negative, but it's less. So it starts coming back up. And then we get to closer to the C value, and we have 0 again because the critical point turns from decreasing to increasing. And we start heading back up. And we take a look at our value at 5. Now they're giving you an estimated slope here. Here they give you a tangent line. They're saying this slope is 3/2. So this point at 5 would be 5, 3/2, or 1.5. Now there's some other things I want to point out about this graph. Again, the critical points are where you go from decreasing to increasing or increasing to decreasing. Notice I have a critical point here, and a critical point here. That's 3. Whenever you take the derivative, you're going to go 1 less than that. Our critical points in our new graph, here and here, are only 2. So that can be a self-check for you. Let's take a look at example 2. Back to doing a little bit of math. The formula for finding the derivative will be the limit as h approaches 0. We have f of x plus h minus f of x all over h. And in this problem, we're going to see f of x, x cubed minus h, and we're going to find the formula f prime of x. Okay, so we're going to use the formula to do that. So let's go ahead and move down here. We see here is our function. We're going to replace everything with x plus h. So now I have f prime of x equaling the limit as h approaches 0, x plus h cubed minus x plus h. And then I'm going to take that value and I'm going to subtract the f of x. And remember, when I subtract, I'm going to change the sign. So this was positive, it's now negative. This is negative, and it's now positive. I'm going to multiply this out, and hopefully you remember how to multiply out your binomials. This is going to be x cubed, 1, 3, 3, 1. So our constant is 3. X will be 2, h will be 1. Plus constant 3 again, x is 1, h is 2, plus h cubed. Okay, and before I go on, I thought I better pause right here and let's go over here on the side and just review Pascal's triangle. If you don't know how I got the 1, 3, 3, 1, Pascal's triangle was what hopefully you learned at some point for finding the coefficients when you're multiplying out binomials, trinomials, or binomials, sorry. Binomials, whether it's to the second power, third power, fourth power. So this is when I talk about the binomial square. You have an exponent here that starts with x squared. The 1 is the coefficient, and this is the 2 that I always talk about when I say double it. So then you have the 2 value here, and then 1 again. Now, this is a cube, so in a cube, our coefficients will go 1, 3, 3, and the 1s always come down the side. So I wanted to review that with you. So that's how I get 1, 3, 3, 1 here for my coefficients when I multiply this out. And the exponents always start with the main exponent starting at the highest degree, which in this problem is 3, and then going down 3, 2, 1, 0, and then the other variable starts with 0, 1, 2, 3. So hopefully you learned that, but I wanted to review that real quick. Okay. Moving on. All right, so let's continue to multiply this out. I'm going to distribute my negative and distribute my negative here. Okay, and all of this is over h. Now let's see, is anything combined? My x cubed and my negative x cubed cancels. My negative x and positive x also cancel. That looks like about it. So now you notice the rest of them all have an h value, so we're going to factor out that h value. And what remains is 3x squared plus 3xh plus h squared minus 1, because I factored that h out. All of that is over h. So now we can reduce the h's. So now I have the limit as h approaches 0 of 3x squared plus 3xh plus h squared minus 1. And when I plug my 0 in, it knocks out these two numbers, or these two terms. So my derivative would be 3x squared minus 1. Okay? And that is example 2. All right, let's take a look at another example. Example 3. F of x is equal to the square root of x. It says find the derivative of x and state the domain. So here I'm going to notice that this would have to be x is greater than or equal to 0 because it's under the square root. So I want to make sure I point that out. And now I'm going to use my formula. F prime of x equals the limit as h approaches 0, x plus h, f of x plus h, minus f of x all over h again. So when I substitute this in, I'm going to take my value that's under here now, my x, and I'm going to substitute it in for x plus h. Okay, so that will mean I now have square root of x plus h. Nice thing is I only have one term. And then I'm going to subtract from that f of x. And again, all of that is going to be over h. So now I see I'm going to have to multiply this by conjugate. Okay, so because I still can't substitute 0 in the bottom, it'll be undefined. So when I do that, I'm multiplying by x plus h plus the square root of x over x plus h plus the square root of x. Okay, so now this, remember, is the difference of perfect squares, so the middle terms will cancel out, leave me with a square of this, and leave me with a square of this, subtracted. And since that happens, my x's are gone. And I end up having oh, I forgot my bottom. I have to keep my bottom here. Let me go over here. Still have the square root of x plus h here, plus the square root of x. Okay, so these are gone. Now I'm going to reduce my h with the bottom, And I have my limit as h approaches 0 of 1 over square root of x plus h plus the square root of x. And when I substitute my 0 value in for h, that will give me 1 over square root of x plus square root of x, which is 1 over 2 square roots of x. And that will be my derivative. Now that I have the domain for my derivative to look at, I have to consider that my radical is now on the bottom of the fraction. So before, x could be greater than or equal to 0, but now x cannot be 0 because it's on the bottom. So x has to be greater than 0 for my domain. Okay, and that's example 2, or example 3. Okay, example 4. F of x (1 minus x) over 2 plus x. All right, so we know that our limit formula is f of x plus h minus f of x all over h. So when we're going to plug this into here, our f of x plus h will look like this. Wherever you have an x, you're going to put x plus h. And the f of x is here. So once we get these two, we'll plug them in. I'm going to go ahead and distribute that negative here through to the h. Then I'm going to subtract my f of x. Now I need a common denominator, so I cannot just add an h to both sides. That doesn't work. So my LCD is going to be 2 plus x plus h times 2 plus x. So I need to multiply this first one by what's missing, and that would be 2 plus x. Multiply the second one by 2 plus x plus h. Okay, well, let's do it. So now I have 1 minus x minus h times 2 plus x minus 1 minus x, 2 plus x plus h. This is all over 2 plus x plus h times 2 plus x. Now I wouldn't multiply that out right now. And I need to remember that this whole thing is all over h. So that means I can invert and multiply, and when I do that, when I multiply this by 1 over h, it's just going to move the h on the bottom. Okay? All right, so let's multiply this through. Here we have 2 plus x minus 2x minus x squared minus 2h minus xh. And then I'm going to subtract from that. I'll put parentheses so I can distribute the negative later. Multiply this by 1, so it will be 2 plus x plus h, and then multiply by negative x, negative 2x minus x squared minus xh. So, distributing through my negative, and bringing the other one down, I will have this. So let's see if we can combine anything. So here we have 2 minus 2, which cancels. We have a positive x and a negative x, which also cancels. We have a negative 2x and a positive 2x, which cancels. Have a negative x squared and a positive x squared, also canceling. And negative xh and a positive xh, cancels. Now I have a negative 2h minus h, so that is negative 3h. All of that is still over. I'm going to move the h to the front, it just looks better. And I can reduce my h's now. Once I reduce my h's, I can then take a look at the limit as h approaches 0. So that's what we're doing here for the formula to find the derivative. So that means I'm going to plug 0 in here. So that'll be negative 3 over 2 plus x. The plus 0 won't be there because I substituted that in. And then 2 plus x. Those quantities are the same, so I can write it negative 3 over 2 plus x quantity squared. Okay, so that is example 4. Now, let's take a look at some different ways to say we want the derivative, okay? Because you never know what notation you're going to see. Different professors like to put it differently. Books put it differently. So let's take a look. So here, f prime of x, that's how we've been writing it for the last couple problems. We have f prime of x. Can also be written as y prime. Can also be written as dy over dx. Now you might recognize this when we had talked about the problem, if you watched it in the beginning of class. I put a video up for you to take a look at about the coronavirus spread. So you might have seen some notation that looks like that. Also df dx. That's function notation there. D dx of f of x. And then just a big D in front of the f of x also means derivative. And then we have df of x with the sub x down here. Also different ways of saying find the derivative. Okay? All means the same thing. The other thing is, remembering that dy dx is the change of y over the change of x, and we're looking at that distance on x approaching 0 as you get closer and closer. The final one, which you don't see too often, is Leibniz notation, where you have dy dx and then you have a line here, x equals a, and that's if you want to indicate a value of the derivative at a specific number. We would use that notation, either like this or like this. You won't see too much variance in this class about it. Okay? I'm going to skip example 5. And we're going to take a look at the theorem, theorem number 4. If f is differentiable at a, then f is continuous at a. Okay, so we talked about continuous functions. If you can differentiate it, then it's going to be continuous. There has to be a value. If there's a slope value at all, then there has to be a value there to begin with. So that is also a theorem to keep in mind. Okay, now, what are some ways that maybe it isn't differentiable? Some ways that it isn't differentiable is whenever you have this corner that comes up, sometimes called a cusp, where you come up and you come down sharply, you change concave up and concave up like this. If I were to ask you to differentiate this at that point, you excuse me, you can't. Okay? It does not have a slope at that point. The slope is not defined at a cusp or a corner end like that. Also, if you're looking at the discontinuity, you can't differentiate it there either. So that's another area where you can't differentiate. And then finally, sometimes you'll have a curve that comes down so steep that it actually has a vertical line. And if you remember from algebra, a vertical line is no slope. So if it's no slope, then it's not differentiable either, because finding the derivative is finding the rate of change, which in essence is slope. Okay? Okay. Now, the next thing we're going to look at, and we're just going to probably look at one of these here. We'll be doing a lot of these later in a different way. Here we had our x cubed minus x, and instead of finding the first derivative, which we already did, if you recall, that was the first example that we did, I want you to find the second derivative. Okay, so how you find the second derivative, and let's go back and take a look at that. That was, I believe, example 2. Yeah. Example 2, we had x cubed minus x, and we differentiated it, and we found out that f prime was 3x squared minus 1. Now we want to find the second derivative, and all we have to do is differentiate it again. So if we differentiate it again, then we're going to use the same method. Okay, so if we do it again, we're going to be putting this time f prime of x plus h and f prime of x. So f prime of x plus h is 3 times x plus h quantity squared minus 1, and this stays the same, of course. So now I'm going to plug that in, and I have 3 x plus h quantity squared minus 1. Better leave myself some room. Minus 1. See why I don't like pens? Okay. And then I'm going to subtract from that minus 3x squared, distributing the negative through, plus 1. Of course, all over h. Binomial squared. Using Pascal's triangle again. X squared plus 2xh plus h squared. There's a 3 in front of it, so we need to distribute through that 3. I'm going to go ahead and write that right underneath. 3x squared plus 6xh plus 3h squared, and then I still have my minus 1. But I also have to bring down minus 3x squared plus 1 from my formula. And that is still all over h. Okay, anything reduce or cancel? Yes, this cancels with this. My 1 cancels with my 1. And that will leave me with 6xh plus 3h squared. All of that over h. We are still looking for the limit as h approaches infinity. And I need to factor an h out so that I can do that. It'll now reduce with the bottom. And now I have limit as h approaches 0 of 6x plus 3h. And when I plug my 0 in, I find out that my second derivative is just 6x. Now, to give a nice graph of that, right here on the page, here is f. And remember before, we had 2 critical points here, going up, going down, and going back up. When I differentiate it, I go from 2 critical points to 1 critical point. And when I differentiate it again, I go from 1 critical point to no critical points. And you would just continue the process to find the third derivative, fourth derivative, etc. Well, can't go etc. because at one point you're going to get to 0. So, okay, wow, that's the end of 2.8. Well, not 2.8, 2.2, sorry. 2.2, lesson 10, and I'll see you for lesson 11.